So, hey, welcome to Coffee Compiler Club. You're being recorded live. If you don't like that, bail out now. Everyone here is most everyone here is an old timer. So anything to do with compilers, language runtimes, garbage collections, typing systems, null and not the null, and anything else to do with language implementations are all fair game. I'll put the video up live in YouTube, generally within a couple hours to a couple days. I reserve the right to moderate, never had to do it. I think that's it. Let me catch up on the last person and we can take off. Cole, I have asked you 3 times and I wrote it down. What your email to Cole, there it is.
Okay.
I think I got you.
Cool.
I've got a question to kick us off.
Yeah, fire away.
So I'm looking at OpenJDK, and I'm looking at the assembler in particular, and there's this label class that I'm realizing is also extremely similar to the label class in Dart, where this is implementation that threads a bunch of links through the code buffer, and then that's what it uses to resolve jumps and stuff when it's bound. What you've been in the JDK a bit. Where did that come from, and who is the initial author, and why are they all the same?
Oh, I don't know why the initial author of Dart looks the same. Although I can guess, although it's not terribly important. The concept is a pass and half assembler, and the pass is you walked over the program text and you spit out assembly code. But many processors of that era had jumps of shorter and longer. Short jumps are common, long jumps are rare, but you had to have them. So you had 2 sizes of jumps. When you put the assembly out, you had to place things physically, and you had to therefore know the size of the branches that you were walking over. So you had to make a choice. And people went both ways here. You could make all branches long, and that was your first pass. You wrote all the code out. It was conservatively correct. Many of your long branches had stupid short offsets. So you revisited every long branch, and if it was within a short range, you made it shorter and you scooched everybody. And if you scooched everybody by making like a system array copy, you get like an n-squared effect as people scrunch up. And then as they scrunch up some more, you can shrink some more guys and they scrunch again. And eventually you had a fixed point. So to do it in a pass and a half, you have a pass where you have a bunch of delta offsets, and you poke people that said, you're a long branch of 4 bytes, I make you the short branch of 2 bytes. And then the people who crossed that branching point can now be revisited to see if they are also shorter. And so you can shrink it down to a pass and a half, and you can go both directions. You can start them all small and force them larger as well. And it gives you technically a better answer, although the savings are modest.
So these don't do that. They don't move any code. They don't adjust any things. They all have this API where you sort of guess, is it a near jump or a far jump?
Oh, okay. Oh, this is the macro assembler.
Yeah. Sorry, the C++
Yeah,
assembler.
this is handwritten stuff. So the coder had to say long or short.
And I just realized also, this is the same label and sort of assembly generation as in Strongtalk. So maybe there's some sort of VM lineage here that's going on.
There is, but it's also, the concept has been around for the dawn of time. So I'm saying it's a 40, 50-year-old concept. But the lineage, I will guess, actually I don't know, I will guess that Robert Brismer walked over to Google, worked on Dart, and recoded things. He did the initial coding implementation, although I sat down on that code and made it do smarter things when I invoked it from wherever. I know I played that game because we're talking 80, 88, whatever, 82, 86, 83, 86. And it was important to squeeze those bytes. Did Aaron just drop in and drop out again? I'm confused. It's fine.
My computer's not very happy with me today.
Gotcha. You showed up half an hour early too. And then I like, hey, dude.
Yeah. So I often will let it join early and then just let it sit in a background, figuring that I'll hear the meeting when it starts, so I don't have to watch the clock.
Yeah, fair enough. Yeah, I get the warning saying somebody's trying to join your meeting, and I'm like, no, it's 30 minutes early. What are you doing? I'm busy doing other stuff. So did that answer your question, Max?
I think so. I'll have to track down the original by Robert.
Yeah,
I hear his name a lot. I still have no idea who he is.
For a reason?
Sorry?
Why are you finding the original author?
I'm not. I've just worked in, so there's for RVM, we adopted port of the Dart assembler, and then I was looking at the JDK for their top of stack caching thing, and I noticed their assembler also is the same API, and then I was like, well, maybe it's the same in Strongtalk, and now I'm just like sort of tracing that through the ages.
Yeah, I think Robert Grismer, he did the HotSpot interpreter 2 or 3 times. He probably had a heavy hand in the original assembler. I certainly was all over the assembler code, but I wasn't the first. So I would start with Robert. So the names I know. There are some other people in the original core HotSpot team that brought the code over from Anamorphic as a startup that Sun purchased. Exactly, it was a support of self that they were going to report to run Java bytecodes. And I'm drawing a blank about other team neighbors. Lars Bach was the team lead. And he's a good guy. He probably remembers the other team members and might know more history too.
Is Lars the one doing the Dart VM now?
Oh, maybe.
In V8?
Maybe. I remember thinking I was hearing that.
I think so.
So he should surely know. There was a core of us that knew how to work that macro assembler really heavily. I mean, you had to. You were generating so much handwritten assembly and machine generated assembly and whatever.
I've been ass deep in the macro assembler for the last 4 months in our project.
Yeah.
So it's just like assembly every day, crashes every day. It was crashing for a month straight on me. It was terrible.
Oh no.
Do you think the assemblers are actually worth it versus just generating machine code?
No, you have to handwrite assembly. Now, are you going to write it in Intel macro assembly language? It kind of sucks, and it doesn't give you the support you need. The macro assembler gives you a ton of support that you can't get anywhere else. So it will track OOP maps. You declare
so to clarify,
register. I'm sorry?
We should explain, this is like a nice C++ API for generating machine code directly.
Yes. And I will claim that the one I did at Azul, which took that, but replaced the x86 assembly with something that looked very much like a RISC assembly, like even tighter, cleaner, sharper RISC-like assembly for what you wrote. But of course, it spewed out x86 under the hood because that's what you needed, or Azul, according to the flavor of the day. Yeah, it's a C++ API. It's a good point. C++ API for writing assembly code. And the assembler will track, for instance, OOP maps. So you declare registers as OOPy or not. So you have a C++ variable that you declare that holds a register. It's AX, BX, CX, DX, your hand register allocating style. You then, and there were some places where you could take the machine would let you very simple rules, auto register allocate the hand assembly, but not too many. So you track your OOPs. So when you declare that you had a safe point, it would have all the OOPs in hand and put out an OOP map for the garbage collector to know where to find the OOPs. And if you had to do inline caches, they had rules upon which pieces of code could be atomically updated with a CAS instruction. You can't cross a cache line. So in x86, of course, the variable length instructions, of course, they span cache lines weirdly. Well, you can't CAS to change an offset to a call instruction as part of an inline cache if it's spanning a cache line. So you have to put no ops in to pad. So it was cache line aware and inline cache aware. And if you put an inline cache in, it would allow a cache line to split between a jump and a target, or a call and a target, but not the jump offset or the call offset. And it had like 5 or 6 other things that you couldn't get from a regular assembler that were part and parcel of validating and generating code that you were handwriting anyhow. And you had to handwrite this code because it was always outside the language spec. Like an inline cache, it's not part of any C language. You can't write this code in C, right? So the macro assembler is where you hand wrote. C1 would use the macro assembler directly. C2 mostly spat out machine code directly, except we shared some of the common backend for sort of complicated stuff I didn't want to deal with that was doing the right thing anyhow. So I think OOP maps came out of the macro assembler anyhow. Maybe inline caches came out of that macro assembler. I'm not remembering clearly, but other things, certainly register allocation, all came out of C2.
You can always do your inline caches, your first pass in inline caches with a side table and do it in C or C++. And then, sort of start generating stubs with the if this jump, blah, blah, blah.
Oh, you're talking about how to implement inline caches? Is it as opposed to how HotSpot implemented them? Just
yeah, you don't need to go straight to the assembly. Like for your first pass, if you just want to test your caching and you don't want to have any architecture specific stuff, you can do it in C++.
That's a cache. Does it count as inline?
It's in, you switch the opcode and then the opcode says, blah, 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 cache. And you're like,
the key is that you have a slot in the cache for every point in the code. So every little point in the code has a unique cache.
You can do that, but it's on the side.
And so then, you can put it off to the side. I agree you can do it. To get the fastest speed, you want it inline. And
yeah, my question is, are you going to take a branch mispredict when you hit those?
Well, it's a bytecode VM to start with, so you're going to have branch mispredicts all the time.
If you're still bytecoding, you're in trouble, so that's fine. You don't care. Yeah. You ought to be able to take a static call to a C++ generated widget, which under the hood does an inline cache, so you wouldn't take a mispredicted branch, but you would take one or two extra branches. You take a branch over and a branch back, all inline, and he has to prefetch through them, so it'll slow him down a little, but not too bad. It's not like a mispredict. One of those is probably free. The second one probably starts to run his instruction fetch pipeline out, because the return will start with a return from a call, go to your stub, and immediately hit a jump and have to fetch again. And I don't know how far ahead he can run those fetches. So somewhere in there, he probably takes a little bit of a stall, but it's not too bad. Yeah, if you're doing a bytecode interpreter, your first cut is to get a JIT going before you care about an inline cache actually being inline. Yeah.
But even in like a template interpreter or assembly interpreter, it's still pretty nice because you can unroll the loop for like a polymorphic cache.
Yeah. Well, you have to ask your performance. See, well, I don't know where you guys are at. I did the performance work a bunch on where to draw the line between JITting and interpreting. And like the bytecode interpreter spends half of its cycles with dispatch after very aggressively working the dispatch logic down. So an inline cache or just a poor ass vcall sort of hardly made a dent compared to getting rid of the dispatch logic.
So let me see what our dispatch logic is right now, because it's not. I mean,
you have to go ask the profiling. You have to go ask the hardware.
It's also something that's changed over time because 30 years ago there was no real penalty to a dynamic dispatch, but as caches became more effective and branch prediction became more effective, it became relatively expensive to do a P-code dispatch.
Yep.
So if you look at VB back circa 1990-ish, they had like a 2 or 3 clock cycle impact from the dynamic dispatch. I mean, it was brilliantly done. I remember disassembling it. I mean, I remember someone telling me about it. And
you would never have done something copyright illegal back in the day.
That's right.
Yeah, okay.
But at the time, of course, 2 or 3 clock cycles was like half a second, so it was a big deal for a different reason.
So we've got a massive 6 instruction dispatch.
Yeah, that's pretty massive. But
it could be 300 cycles.
12%.
Yeah,
12% well,
If it has
how do you know 12%? Where do you get your 12% from?
So we're looking at a Colgrin profile of the whole program, and it's like say 10 million instructions for a benchmark, and then you look at the thing, and it's like, well, 12 million instructions, you do X many opcodes, and it's 6 instructions per opcode.
No, right. So it's all wrong. You've been lied to, and you don't know it. So that's the double fail. Both you've been lied and you didn't catch it. So
Okay, so we're just measuring instructions right now. But
yes.
if we're talking about caches and cache performance, I understand that's a totally different ballgame. But right
Okay.
now we're just measuring on instructions to
So
keep it simple.
the cache that you're worried about is your branch target buffer, which will have been completely slammed and overloaded and not doing anything useful. So every one of those jumps will be 30 clocks. So count them as 30 instructions, not as one, and redo your math as to what percentage go to the dispatch. You say go count your indirect branches. They are, and I say 30 clocks times 4 wide issue. So roughly 100 instructions, really. That's where your cost goes. And if you don't do a hardware performance counter, it won't show up. And if you're just counting, I did 10 million instructions, of which X fraction were branches, I give them this percentage, that's a complete lie and a big one. You redo your math and I'll bet you'd come to 50% or better.
So yeah, I mean, I'm in the middle of doing a template JIT right now. So
yeah, okay.
Well,
okay, so wait. So this is important, but maybe you won't believe it, but I've been down this path a bunch. Know where you're starting from so that you can tell when you've made performance, when you've made progress. So get the number for the jump branching. Either take my 100 cycle if you want to trust me, and if you don't, get a hardware performance counter going on there, vtune, and ask the question again. Then get your JIT going, and then go look again, and you'll see the difference, and you'll know why the difference is why it's there. And that's the key, Pete, is to know that it's there and know why it's there, and then you can plan around it. Because that'll tell you when it's time to take your outline cache and make it inline, or to have an inline cache at all.
So it also begs the question then, at that point, whether it's worth producing an efficient JIT code versus interpretation. So just across the board, do you dramatically simplify your implementation? What's the cost of JITting everything?
Yep. So, right. You want to have a good cost model for your effort to produce a JIT versus the gain you got from, living with.
And I'm curious if anyone has any experience with what the size the memory difference is, the footprint differences between a reasonable bytecode and a reasonably bad JIT.
Yeah.
So speaking of inline caches.
I'm sorry?
Speaking of inline caches, the inline cache model in a JIT I'm familiar with is you unroll it. So it's just like, if you're this hidden class, you do this thing. If you're this hidden class, you do that thing, and for like a method dispatch. But if you have like an attribute offset cache into the object, or no, sorry. Yeah. So for method cache, if you have an attribute offset cache, it's like an int. But if you're having like OOP addresses in your JIT, how do you, and you have a moving GC, is there a model for like updating those pointers?
Yeah. So in the land of HotSpot, we went through all these directions all at once. It kind of sucked. So if you put code OOP pointers in code, which we totally did, on an earlier x86 with 32-bit VM, then you told the GC that you had an OOP in the code, and the GC had to atomically patch the OOP and had to be aware that moving code was going to cross the patch point or not. So atomically patching meant somebody got the left or the right version. And now you have to decide if your moving JIT was stop the world or not. If it stop the world, you were fine. You stopped everybody not in the middle of grabbing that you had a load immediate of some kind. Compare immediate against a class pointer was the obvious one. You did inline cache, you did a load immediate of a load 0-word header to get the class pointer. You did compare immediate against a constant in the code. If they were unequal, you went to fail land. If they're equal, you did a static call to the inline cache. So that's the inline cache, fast path, 32-bit VM. The difficulty, of course, is you can't patch the compare instruction while the code is running unless your GC is very much aware of it and has all the invariants in place. Also, your code lifetime has issues because somebody might have compared against the old version of the compare versus the new, or the new class pointer, the old class pointer, and then be frozen by the OS as a not at a safe point for some long period of time while the background GC threads immediately shuffle the heap. And then it restarts with the decision already made based on the old class pointer, right? So you have to be aware of these subtleties going around. what I did at Azul to make that life get a hell lot better is I cleaned up my object headers to have a class ID instead of a class pointer, which shrank the space
That's what we
from
have.
64-bit VM down to 19 bits, 20 bits. You picked some threshold on there. You had a million unique classes, or 500,000. It was plenty enough. And now you're comparing against bits that aren't moving, and you get rid of the whole moving GC patching pointer and code thing. The other thing going on is that instead of trying to load a 32-bit VM, an x86, I think, would eventually let you do 64-bit, but you couldn't atomically patch it unless it didn't span a cache line. So you couldn't have a moving GC and a non-stopping GC, other than stop the world one, because you couldn't patch atomically. Okay, fix all that by putting those oops in a table. You put a load from a table offset and table base and offset. And the table, it's just like an array load. It's entirely predictable. It's one extra indirection layer of cache hitting if it's going to be common, and you can schedule it in the hardware and the JIT. And now you have a big old array off the side. It's got global pointers that the code is managing, right? And the GC just has a big old array, and it just does array-like things with the big old array. It's very happy.
That's pretty nice, actually. So
yeah.
you're saying one big array shared by all of the JITd functions.
Yes.
And you just put an index into the code.
And you skip the whole patching code with GC. We did.
Does that array move?
I'm sorry?
Does that array move?
We just made it big and declared that you can't have more of these pointers in, like, we didn't map virtual space for it, but we declared it was fixed size and large because it was not constants in the entire code base. It was constants from the JITted code. And you didn't JIT everything, and not everything showed up as a constant. So you didn't need it to be huge. I mean, a big, busy web server kind of thingy might have a few thousand of these constants, but it wouldn't be having billions.
When you say constants, do you mean like 5, or do you mean like a function that?
No, constants like oops, a string pointer to hello world, the pointer to the string hello world. I made the golden instance of the JBoss top level container class, or the top level or whatever, all the decisions, high level decisions class, whatever. I loaded the configuration class or whatever. You get all these golden instances of whatever. And people are asking the question, do I have the golden instance, and what am I doing with the gold? And when I fetch which flavor of GUI display model I'm showing you, swing versus JavaFX versus what, I don't know what. Everyone had different things there. But these were, like I said, modest count. Typically, you get a couple per method. You compiled a few thousand methods. You had several thousands of these things, but not millions.
Do you make any effort to deduplicate entries in that list? So like if,
Totally.
So when you're generating the function, you go scan through the table. You're like, oh, if it's this, then this.
Yeah. You just hunted the table. This is at JIT generation time. You had a couple thousand entry table. You just a fucking linear scan. I mean, you could get clever and do a hash table or whatever that was backed by a fixed array that the GC just treated as an array and blah, blah, blah. I mean, that non-blocking hash map, I would totally do that. It's a fixed size array. If I don't blow it up, it doesn't move. The GC has a fixed array. We're all happy with a fixed array. And then I can hash also as a shortcut. But a few thousand entries once per JIT, linear scan.
Yeah, if you do the split table that CPython does or whatever, the split hash map, that actually makes a lot of sense. You have your indices, you've got your, so they do this thing where it's not like just buckets. You've got like an indices array and you've got a values array.
Yeah, I do what's called I think an open table. I have an array. There are no buckets. If you collide in the array, you skip to the next entry in the array.
Open hashing.
Open hashing, thank you. Which means it's just an array, which means everyone who does array-like things can do array-like things on it. So you can linear scan it like an array, or you could hash to find a shortcut to where you think you're going to land, and then you linear scan forward and yada, yada, whatever. So there's ways to do it. But the main one is we got the code, the oops out of the code, because that was such a pain in the neck for weird, bizarre lifetime interactions of when I wanted to delete the code or do something, and the garbage collector trying to move things, and threads that had passed over an oop had picked up either the old or the new version of your patching and then got blocked by the OS for some length of time, and then appeared magically later, now very, very stale. You had to force them through a safe point to know that they had picked up the old or the new version. And that was one of the many subtle bug things that was, you only crashed rarely. But when you became as popular as Java did, somebody was crashing all the time. Pain in the neck to debug those.
I think our initial plan was going to have all the threads sync and do a stop the world GC, but then eventually move to concurrent. And
Yeah. No,
but
that's a good starting point.
the last thing I want to do is any code patching, right? Like, this is my first foray into writing a JIT. I do not want to patch code. I just do not.
So the macro assembler lets you patch code safely. An inline cache is patching code. A macro assembler gives you big handholding for that. The other piece that comes in with that is that you do end up with static calls. The JIT can determine this call is static, but when you start, he doesn't have a JITted target, so he just calls into some interpreter stub, which would jump off and go in the interpreter. But when you get the other guy going, the next time that call makes and he goes to the interpreter stub, that stub should do a lookup and say, hey, there is also a JITted version. I'll look at the return address, go back to the call site, patch it to go direct and get rid of the bounce, right? And you do that in lots of little places, all of which turns into code patching all the time. So you want to have a hand holding to help you code patch, and then it becomes easy. Like, don't run away from it, engineer your way through it.
So what we have now doesn't require code patching, because the things that we have, all functions have like some entry point that's like some pointer. And then when you JIT a function, you replace that entry point with the JIT pointer. So it always just does a direct.
So somebody has to grab that
it.
pointer and then jump. And I'm saying, when you go JITted to JITted, you ain't grabbing no pointer, and you get rid of the indirect jump. And that's the key. That's what I'm talking about, the branch target buffer. That branch target buffer, that only works if you only have a few things using it. If everyone is taking an indirect bounce through an indirect pointer, that branch target buffer will get totally slammed, and every one of those will be the bad case mispredicted branch call. You really want static to static in the end.
So if you have a JIT to JIT caller and you're going to go patch the address, like you've done this call, maybe you're in some stub, maybe you're in the JITted target function. Yeah.
How do you do it?
How do you?
How do you do it? Okay, here.
Yeah.
It's not this. You do it once and you figure it out. There's no magic tricks, right? These are all things that just do done.
But there's nicer APIs and there's shittier APIs, and I'd rather have the former.
Okay, no, that's fair. So the first thing is you took a call to one of your funny entry points that knows something special is going on. So that entry point starts out with being one of these piece of hand roll assembly that you're going to use the macro assembler for. And he wants to test somehow that there is a better option, or he's going to jump to the interpreter. So he's going to load something that says, this is where I want to go to. It happens to be interpreter entry point, and I'm going to do a jump register. So somewhere he loads, and then he wants to test a bit, saying, oh, but wait. Okay, so if he goes to the oh, but wait path, then you got a bunch of options. An easy one is to say, call back into the C++ code with the return address, which I have to have machine code. So I'm assembly writing. I just go fetch the return address because I just took a call in. I know my whole calling convention of the assembly code. 3 spots back on the stack, that's the return address. Fetch the freaking return address, put in a register, call into the VM, call into your C code. Now you get a C called function. He's got a return address passed into him, and he's got the target method he's trying to go to passed into him. He knows behind the return address, there should be a call instruction. So you go ask the macro assembler, please, Mr. Macro Assembler, verify that you see a call instruction. There's a little assert that you just catch your bugs, and know that because the macro assembler put that call out, it's patchable. Atomically stuff. And the macro assembler has support here. It says, I see a call. I'm told here's the address of a call. You took the return address, you -5. That's the address of the call. Here's the call. Here's where I want it to go. Maybe here's where I think it's going now. And you don't really need that piece. Please atomically update it. And the macro assembler, you just handwrite the little code in C++ that says, CAS, validate, verify however you want to, trust yourself, and then done. It's patched, and you get back.
So I guess right now we only have a call register and a call 4-byte offset. I don't even know, there's not a call keyword.
No, you only do 4-byte offsets. All your code lives in 4 gigs. So you pick a code cache, we call it a code cache. You name the 4 gigs. This is where all the code lands. It's not hard. You set that aside. That's where you're putting your code. And now it's all patchable. It all had to be that way in the first place. Anyhow, like your VM, you actually wanted your VM in the same 4 gig space, so you wouldn't ask what the 4 gig space was, and you malloc some space around for your code cache. You give yourself 100 megabytes or something out of the 4 gigs, however much code space you want.
That's what I've got right now. I just mmap a gig and
yeah,
demand page, blah 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 blah.
Yep. So mostly all the patching calls were rarely patched in the assembly directly. We usually went to C code with the patch address somewhere available so that we can now write high-level language things that did assertion checking and the like, because obviously you screw this up and you crash horrible death. Every assert you can throw in there is much easier to quickly nail down what's going on. Inline caches have a lot more states to them and are a lot trickier to patch. But once you get the concept is that I can jump into some C code, validate the state of the world, do something special, atomically update, validate the state of the world, and get back out, then you can start to expand your repertoire of what you're doing.
Yeah, right now, if we have a IC state transition, I just deopt and I'm done.
Yeah, no, I can step you through that one too. There's a real state machine that you need to think about, because there are some transitions that require deopt and nearly all of them do not. So
right now it's like about, we have this bytecode that we keep on the side, and then we've got the JITd code. And I didn't want to think about like, okay, we changed the bytecode. So we flip it from monomorphic to polymorphic. And then we also, patch some instructions, like we add another compare jump, blah, blah, blah. It's like, I didn't want to, not for the first implementation, but maybe later.
Yeah. The first thing goes on here is that depending on your language spec, polymorphic versus monomorphic might not help you as doodly squat compared to getting a JIT. Like, don't bother making a pick until you got a JIT.
So the pick helped a lot. It was like a 20% in terms of CG instructions.
Okay, I would look at your overall runtime and look at your dispatch costs. I claim you should be staring at it with a hardware counter if you don't trust my 100 clock estimate, which it's a little out of date. I suspect it's not gotten any better. It might be low, but throw a hardware counter at it and see what you get. VTune.
Yeah, we've got a
both a hardware counter and a wall clock. Ultimately, time is your oracle.
Ultimately, you have to do wall clock, right? But he's trying to ratio. I have X% jump instructions and 100 minus X% of everything else, and have a wall clock time. Okay, he's trying to blame. Who do I blame here, right? So
no, so that was not for wall clock. That was all in terms of CG instructions. And so we're doing that as a rough estimate until we get really fine tuning, and then we're going to do some of the other stuff.
You should do wall clock only from the start, because wall clock is the only thing that really matters. Do not, literally do not. You can count, x86 add instructions to your heart's delight, and every time you do a mispredicted branch, it didn't matter how many add instructions you counted. They don't count for nothing. Wall clock. Go.
Do you have a quiet machine setup?
Physics matter. Wall clock time, hardware counters. Get your ground truth. With your ground truth in hand, now you can make better design choices. Picks look good on paper. My experience for Java, which admittedly, not the world, picks didn't count for doodly squat.
If you have are you telling me the 20% reduction in CG instructions is nothing?
If it didn't count against the instructions that matter, it didn't count. Yeah, exactly. If you took 20% reduction,
or a bunch of hash table lookups.
If 50% of your time is spent doing dispatch, and you took the other 50% and took 20% off of it, you got a gain of some amount. If you went to the 50% and you took 50% off of it, or 100% off of it because you got a JIT, you get way more gain. Go break down where the time goes. Now, if you have a language that does a lot more megamorphic call sites, maybe the pick starts to make sense. But you have to be megamorphic in small count for it to matter. Like Java's
Yeah,
megamorphic
it's
in
mostly up to 4.
If
like
your language
70% up to 4.
commonly dispatches at one target only, like Java does, then the inline cache of 1 is great, fine. If it commonly dispatches to 50 things, 4 ain't worth squat.
It's up to 4 is mostly.
No,
it's
I'm
like
not saying
90%.
that. I'm saying if the language and the way people use it commonly take a 50-way dispatch, like they're doing Ruby or
Yeah.
something crazy, one of these other guys, they will
No, we
commonly
measured.
have megamorphic call sites that go 50-way, right? Then a 4-entry cache will not touch the 50 and you'll get nothing out of it. It'll waste your time. It'll be negative because you'll do all these tests and fail and go the hard way anyhow.
Yeah, though we took a
Right.
look at our web server benchmark and we measured, and it was
I mean,
like,
that does depend somewhat on the distribution of the 50.
It
If it's
does.
50-way megamorphic, but
No,
90% of the time it's the
Right,
first
right.
one and 9% of the time it's the second one.
Right. And if you beat down the times that you need to use that branch target buffer, then the x86 will rescue you on those. The one call site, you take the inline cache correctly 99% of the time, and the 1% where you fail and you go megamorphic, the branch target buffer gets it. That's what you're trying to get out of that. But that BDB will fail if you have everybody touching it and they're all going different directions. It'll just blow out. So I'd say start from wall clock and a solid understanding of where your time goes, because it'll be highly lopsided on your instructions. And then decide, yeah, I need to do this or that or whatever. And, then I think, doing a template JIT's a good first cut. And then, but I claim your pick counting is highly suspicious. My bad smells nose is going off here.
I mean, we also have we have a per diff perf thing that does, God, it's got call grunt, it's got wall time, it's got, what's it called? gperf.
Well, you have wall time before and after your pick.
Yeah, and it was lower.
What did the wall time
Roughly
say?
rough correspondence to CG instructions within 10%.
Really? So 20% wall
5%.
time improvement.
It was big. It was like
Okay.
slow before. It was real slow.
Well, big was 20%, or big was, because you should get a template JIT should double your speed over that.
So I have not finished the template JIT. It like can add numbers together right now. Right.
No. Right. And let's just say if you go look at your dispatch logic, like HotSpot got our dispatch logic down to 4 instructions from 6. Now, took some amount of miracle work, but it was there.
How do you do that? I mean, I can go through ours right now. Ours is like.
Yeah, you've beaten on it a long time. I don't know what's your bytecodes look like.
It's 1 op arg, and then sorry, it's 1 byte op, 1 byte arg.
Yeah, okay, so it's even better. Yeah, we had a pointer to the bytecodes and a pointer to the bytecode table, and an x86 will do load a byte plus plus in an op, and then you do table fetch from the byte with the table base already in a register, and then you do a jump register. Yeah, I think you can skip that. You should be able to get it even tighter.
So we've got move ZBL 2 times, so load op, load arg, and then increment, and then
the arg doesn't count on your dispatch.
What do you mean?
Don't count the arg against your dispatch logic.
That's then we've got 4 instructions.
Does. I'm sorry?
Then we've got 4 instructions.
Oh, there you go. And what are they? They're load that byte.
It's increment.
And
so
increment.
Then, so the next 3 are, so we've got table of these template handlers, whatever.
Increment the IP.
Yeah, he has to increment his IP. He has to
so increment the IP. And then we've got, so we zero extended the, zero extended.
Yeah.
Whatever, extended the op, shifted by some amount depending on how big the handlers are sized, and then
you do it that way. Okay. Yeah.
Add to go to that handler and jump.
Okay. Yeah, you have an extra op for shifting, which is fine. There you go. So
could
you're at
probably-
4 if you don't count your load. That's where hotspot was
Yeah,
at.
and
You could
definitely
probably do an
don't
LEA
worry.
instead of a.
Don't worry about the
Combine the
shift
shift add.
because that's a zero cost.
Yeah,
The op disappears
yeah,
inside the CPU.
yeah. Yeah, I didn't count the load arg and hotspot because it was variable args, and different bytecodes would now fetch 0 to 4 more bytes. And so everyone was different.
We just fetch it ahead of time because like most of them take an arc.
Yeah, and then I think hotspot also has a table like you're talking about where the handlers are just fixed size, and if they need more space than once you fixed, you jumped again to a fatter handler. So
That's what we do too.
We must have had a shift in there too. I'd have to go look now. I don't remember. I know we got it down to 4 though, so fine. There you go.
I
And
assume
that
this
was-
is
like I
a
said, that
stack
was-
machine if there's that few args most of the time.
Yeah, it's a stack. Oh, yeah. I don't know what's your machine, Max? Is it a stack machine? Stack machine, yeah. Okay.
Yeah, we haven't gotten to the point where we're like doing register allocation in a function. Like again, first template JIT, and it's me writing it, so very simple.
Well, you could do a register with an infinite register pile, register allocation on an infinite set of registers, right? And actually, limit it to 65K or something, right?
So,
Yeah,
so
fine.
Max, what is the argument? The second byte.
It depends on the opcode. It's like maybe the number of function arguments being passed to the function. Maybe it's like a jump
Field
target in
number.
terms of like byte offset in the byte code.
But there's always one byte op and there's
Yeah,
always one byte
root for
argument.
one. Yeah.
We also have another 2 bytes for the I cache index, inline cache index, because for the side table. But
So it's technically 2 or 4 bytes.
it's always 4, but we just only load the first 2 and then instructions that have.
Oh,
a
I
cache
see. It's always
load
4. Yeah. Okay.
Yeah.
Yeah. Java having the entirely variable count made it difficult to do a bunch of things. Going to like a 2 or 4, like you want to have a table of counters so you can count bytecodes or backwards branches or whatever. And where do you put the table of counts?
Yeah, compactness and performance are not
Yeah.
jointly.
Yeah,
they're not simultaneously achievable.
Here they fight. You go to a template JIT, you can now do the performance counters at least without the giant extra overhead because you can pre-compute where you're going to put the counter as part of the template, which is one of the reasons I got out of the interpreter and into C1 as fast as I could, is because you couldn't count in the interpreter efficiently. So you only counted backwards branches for the whole method.
I've got the dispatch. It's an interpreter macro assembler dispatch next.
Yeah.
I'm pretty sure this is it.
There are 2 pieces of the dispatch, so you could schedule them. So dispatch next, and there should be I could actually pull code up. Go ahead,
Is
read
it
it out.
dispatch next, dispatch via?
Well,
Or is it dispatch
so
base, dispatch epilogue? There's a lot
It
of
might-
things actually.
yeah, there might be a dispatch base, dispatch next. The table was cloned 5 ways according to the type of the top of stack.
Yeah, we don't have that.
Yeah, the minor gain, it gives you a little bit.
This is a load unsigned byte. So it's a macro thing. Load unsigned byte from an address,
Yeah.
increment, and then dispatch base, which dispatch base does. Oh my God, that's a lot of instructions. What the hell?
Yeah, but start weaving through the if defs.
I don't know.
I have to
What's
go pull it up.
LP64?
I'm sorry?
What is LP64?
Oh. I have to look
Long
up
pointer?
now. Yeah, it's load of 64 or something. There's going to be a load. Yeah, oh, it's in, yes, but what is it? It's like the if def. It's like you're running on a 64-bit VM or something.
That's a pointer. That's a pointer model. So the
64-bit
LP means the long is 64 bit, a pointer is 64 bit, and there's like other data model. Yeah, data model.
Yeah. So it's the if defs according to your building it.
4-bit?
So on Linux, the on Linux long is 64 bit, but on Windows long is 32 bit. Long is 64 bit. So you have to make sure that your code fits this kind of data model. Otherwise, you may run into some kind of problem, some kind of wrong code. Yeah.
You C predated whatever int64 as a common thing. The HotSpot source code predated int64 as a commonly available integer type. So LP64 is a thing which is the both pointer and longs are 64, and the register can be used to hold either. Now you got me curious. I'm gonna pull the code up here. I haven't looked at the macro assembler in forever. Source, is it under CPU or share?
I'm in CPU, source hotspot CPU x86.
Yeah.
So Max, what's the name of the project you're working on?
It is not public, and the name is hotly contested internally. I want to name it after a particular fictional cute animal that people are really not happy about.
Avoid copyright though. Like
Copyrighted,
Sun called their container system Kevlar, which ended up making it much more difficult to open source.
Yeah, we had that issue with a particular brand of containers for food with another project at Facebook.
What file you're in? Mac?
Are you still at Facebook?
Oh, okay.
Probably shouldn't have said that. Yeah, I'm at Instagram. We moved.
All right. Were you looking for dispatch? Prologue, nothing specific.
Dispatch under next and dispatch under base.
Base, yeah, base says verify FPU if verify activation, if verify OOP, load effective address jump. I only have it as 2 instructions.
Wait, where are you seeing?
I'm on interp masm. I'm on the JDK 7, so old source code.
Oh, I'm on master. Hold on. JDK 7. Do you have a link?
No, it's my private copy from eons ago. JDK 7U, I don't remember the number exactly.
I'll find the GitHub link.
But I'm sure the code has here, the code will not have changed much. Plus or minus some copyright lines at the top, it will be all roughly the same.
Interp masm x86.
Yeah, I'm on, and the 64-bit, interp masm x86 64. I'm on line 463, which says Leah R scratch external address table.
So this does not exist in the JDK mirror on GitHub, which actually hasn't changed since 2012. So maybe that's a problem.
I have a copyright that says 2003, 2011 Oracle. And I ran to dispatch base.
Okay, what file are you in?
Interp masm x86 64.
Wait,
That's
source share.
Source CPU.
X86. Oh, I don't have a CPU folder.
Oh, go to the x86 version. That's what you put the link on.
Yeah, okay, so I set the, okay, I'll go to my original.
Hotspot CPU x86 interp masm x86. That's, I'm in the 64-bit version. Let me go to the non 64-bit version, see if there's any different here.
What's the 64-bit version called?
Under 64. I don't have a non, I have a 64 and a 32.
I just have under x86.
And that's funny. Yeah, the 32-bit version is also 2 instructions, but they're not so tightly wrapped up. There's a bunch of extra syntax to spell it out. This is 2 instructions, one to build an address, and then the one of those should be a load, probably the table, followed by load from the table and jump. So that'll be 2 instructions. One will be a jump, one will be a table load, a Leah.
Doesn't look like my stereotype of an assembly language, but fine.
Yeah. So let me show you something else here. So right above this code,
Much more readable, let me tell you.
Yes. So here you see some C++ code that says if verify activation frame generate a label, move RCX to BP, subtract pointer size from the SP, compute a constant in C++ land of the min frame size, compare if you're out of bounds on your frame size, then stop, else just skip around the stop. So that
Also,
emits
for other
assembly
readers,
code that
goes right to
compares a
left.
few instructions and jumps. So if you're saying this is what the assembler looks like, the macro assembler looks like. I write, you know, there's a lot of verification that you can turn on or off when you're debugging the initial interpreter. Yes. And when I went to Azul, I replaced all that syntax with very specific, like move and load for and kinds of instructions. It was always right to left every time. The only correct operand order, yeah, I did right to left every time. Cleaned them all up. There's a bunch of alternative, like the original assembler had these staged things where you could declare an addressing mode, which would take some base and some offset, which is usually a constant table, and some other register with a shift or whatever, and you could build parts of it and keep them and you reuse them. It was kind of clunky. It was much easier just to like have a load for, take what you'd expect out of an assembler. It had a target register, source, offset, which could be a C++ constant, and a second register and a shift amount as the worst case scenario for x86 kind of things. But it's C++, so you can screw around with your syntax a little bit and get something you like. That was the main key out of using that.
Also, you get all your constants for free. You don't have to like you can bake in addresses from static functions that you align and
Like
great.
frame : link offset minus frame : interpreter frame initial SP offset. What are those? Well, I have a frame structure that describes a virtual interpreter frame. And the interpreter frame has a back pointer, that's the link. It has the frame base, it has a frame height, it has some overlapping registers that are passing as args. It has some extra registers, which were new for just this function. That's known stack size. It's still a stack machine, but we know how big the stack's going to be. So we preset the stack and whatever. Those are all C++ constants floating around the world. And you have a giant ass file somewhere that describes that layout and has C-struct things. And you just grab the pieces parts when you're generating your assembly. Much easier to generate assembly this way than to do it with a classic old school macro assembler.
What do you do with comments? There's a bunch of comment constructs I'm noticing called block comment. Where do they go?
I'm sorry, what was it called? Like comments?
Block under comment is a C call.
Oh.
Where do they go? Do you have dwarf stuff?
I didn't, but people had mumbled about that. We tried. I'm not finding block comment in my version of source code. Let me do a wider grep here. Is it capital B block?
Lowercase.
Lowercase block under comment. I got something. Pound define block comment, which is almost surely going to be an inline comment, but I'll hunt for some more here. Patch template. Yeah, these are things that you could find if you look in the code. Almost surely this is jammed in the code as a skip around. But if I'm just spewing code out with a disassembler, you'd find it. There's a disassembler that goes with this, right? That was a key gizmo.
We don't have that. I inspect text,
yeah.
I have like an animal.
No, well, yeah. So you wanted a disassembler that understood your specialness, like your instructions. You'd like it to disassemble pretty print the way you emitted them, roughly. But if you were to put a block comment, you wanted to print. But if you put an inline cache, you wanted it to say, I looked at the code, which included a meta table off to the side. The meta table off the side said, and here's your inline cache points, and I'll break you out the parts. This is where you patch your branch. This is where you patch your call. This is where you patch your clash or expected or whatever. Here's all the patchable call sites. Here's the OOP maps. Here's the layout of registers of being OOPy or not OOPy at each save point, things like that. So the disassembler was, the inverse, not entirely. It wasn't, you couldn't by ejection, but they tried hard, or I tried hard, especially at Azul. I tried really hard there. Block comments were jammed in the code as part of the metadata. So the disassembler could spew it out. Like if there's a thing that says, dump all the hand-generated assembly. And all the hand-generated assembly comes big. You get lots of it. It spews out. Well, the disassembler is all disassembling that. That's your spew out. And along the way, he'll throw in those block comments and you can search for them. And that helps you just track stuff. Debugging aid only. I'm certain. I'm still looking for where block comment is defined. It's probably in the shared code. And that's why I'm not finding
I'm like 4 pages deep into search and I cannot find it.
It's almost surely in the shared code here. And I am, here's my bigger grep. Yeah. It's in the abstract assembler. Share, source share VM assembler, assembler CPP. Block comment says, if your section is code buffer section instructions, do code section outer block comment. So there's a block comment in code sections, code buffer. Code buffer is an annoying thing, but fine. It's you're always it's your linker step. You're always relocating the code from where you generate. You generate it in a buffer that's a standard array doubling buffer. So the buffer keeps growing as you generate code. So you can't put in fixed offset, not fixed. You can't put in absolute offsets because your absolute addresses branch around. So every time you have an absolute address, you instead mark it as this is a relocatable address, and I'll give you an offset from the start of the code buffer that I think it's going to go to, or whatever you're going to do there. And then you generate code and you resize this buffer as it grows, and it doubled out and it finally quit, and you got it in its extra size, and then you want to trim it and relocate it one more time into the code cache and patch all the patchables as necessary. So there's a bunch of one-off patching things that had to be as part of that move and patch, which all you've inherited. If you picked up that macro assembler, you inherited all that. And included in there would be things that, like, we broke out the block comments and we broke out the inline caches and put that in the metadata for the code cache. It's a, you know.
Yeah, I am not finding this file.
Okay, which file are you talking about here? Where I found the block comment?
Yeah.
Okay, it's in source share VM ASM / assembler.cpp. grep is your friend. I have all these fancy schmancy IDE, IntelliJ, Eclipse, go find the source button, blah, blah, blah. grep is your friend. grep is fast. grep is stupid. It will not make mistakes of that kind.
All right, I'm cloning this thing. I was searching on GitHub, but
oh, you don't have it. Oh, you're GitHub. Yeah, I don't know what GitHub does here. There's a lot of funny macro expansion games that probably torment sort of the standard IntelliJ to the end. Is this it? Code buffer. That's code buffer. Now that's the next piece in. I went from the ASM, which just forwarded to code buffer. Block comment. Print block comment. Yeah, product return. Yeah. Okay, fine. And now code buffer CPP. Almost surely has a code. There's an ASCII gram at the front where all the, you know, the layout of the structure is.
So that adds it to an array or whatever.
Yeah,
it's code strings that add comment.
Comments add comment. Yep, that sounds good. Somewhere in the world that will be spewed out when the thing gets finally copied into the code cache. It'll appear so that for the disassembler, I don't know about Dwarf, but the disassembler will find it for sure.
Okay, that's another question I had, and I'm sorry for everybody. I'm completely dominating this discussion, so please, other people.
Usually I do, so it's all good.
Okay. So you can do a GDB extension, and you can have all these nice things. So GDB can unwind your stack and then, like, poke at your source lines and whatever. But
not really, because GDB can only recognize like regular stack traces, right? But C2 or C1 generate some kind of very weird stack traces. So sometimes GDB run into kind of like unknown area. So they just give up. They say display some like
you can provide a C function
marks
that is a hook that'll unwind your stack. So you can write the function that does the unwinding.
Certainly.
Yeah, exactly. Yeah, there's like a PNS in the debug.cpp can unwind and JITd code. Yeah.
yeah, back in the day when I was coding it, I used GDB and we had it unwinding generated frames, definitely.
But if you want to have like not just GDB support, right? Someone I used to work with kept talking about dynamic dwarf, where you generate a bunch of stuff and then you emit it somewhere. Do you have any idea what this is? I cannot find a reference to it online.
Nope.
Okay. Shit.
You got a Dwarf Debugger that you want
Yeah.
to work.
Yeah,
Yeah.
what is dynamic dwarf? My understanding is that's usually
don't
made
know.
by the compiler at compile time.
It's like we would emit it at JIT time, apparently, presumably.
Oh,
But I've never heard of this thing.
oh,
I cannot find it.
Yeah, I have heard about emitting. There's some way that you can have a way to tell the debugger that you've added new dwarf code. This was added after I left to Java or some piece. I don't know where it was happening. Somebody was trying to make dwarf work with JITting. They wanted the debugger, which would otherwise read all your debug info at the startup, deal with the fact that new machine code got generated. It had to now inhale new dwarf. And I don't know, I wasn't part of that. Sorry, I know it happened.
I mean, it sounds like a good idea.
You know, debugging this thing
JDK is a dwarf parser.
kind of pain in the neck. So, well, you had a dwarf emitter, not a dwarf parser.
All I see is a parser. I don't know why.
Okay, fine. Then this is not. Yeah, this is after I left.
Could I ask a quick clarification question? Something I've been curious about with JITs needing to do patching for like the PIC, the PIC. I've always kind of heard, you've got like page markers that the kernel will say, okay, this page can be written or this page can be executed, and usually you don't do both. So you would need to flip-flop the page from write to, or from, executable to non-executable to write it, then back. So do you need to do like a stop all threads to make sure nobody's executing that page? It kind of seems like a global stop.
Depends on the OS.
Ding.
Because in Windows, you have alloc CS to DS alias, which gives you back a pointer that you can use to write to the code, but you don't have to stop executing, and my memory's crap, so don't trust me.
Okay.
I know that we went through various hoops to say the code cache is patchable. So the C code would be execute only, but the code cache would be execute and write. And the rule there was, if you blew it, you blew your security, and, flaming death for all.
And then there's something newer too, Cliff, because after you wrote C2, they added what's called an NX bit. AMD, I think, added it in like 2006. It's a no execute bit. And it's called the NX bit. And so it's basically hardware protection for pages that contain code. And I don't know how that affects this.
Okay, yeah.
So if I'm on a CPU that has a separate instruction cache and data cache, do
Oh.
I need all of my counters to live not too close to my code? Because suddenly I'm going to update some counter saying I entered a basic block. And that's now going to mean that I changed a thing which invalidated a cache in my instruction cache, and I have to reload the instructions.
No. Almost all instruction caches are not coherent with the data cache. So in particular, all these games I talk about with code patching, you always follow it with an iCache flush of at least the line in question. Or the
You have to ask for an iCache flush.
Yes, you must ask for an iCache flush, or the iCache will not ever see your patch. Like the next time
that seems like an easy bug to write.
Yes. So that's why you throw all these things in one place, the macro assembler, and you let it do it. But you don't rewrite that code every time because it's too complicated and too subtle. It's not complicated, it's just too subtle. Too many stupid bugs that you figure out much, much later. That one was a bug. There were a bunch of them with register window based hardware about when they flushed and reloaded registers that would be subtle bugs. So if you had register window slots on the stack and the hardware would spill the register windows when it needed to, and when it didn't, and you wanted to stop and do a GC, the GC valid bits who might be in hardware registers never flush to the stack, and you look at the stack slots and they're garbage, or they flushed them once and you're busy patching them, and then the hardware side, for whatever reason, he took an interrupt and came back, he prefetches and reloads half of the patch. And then you finish patching and he has half patched and half not patched. All these kinds of models interactions. You have to assume like the hardware reload of registered windows is entirely unpredictable and asynchronous and will happen a million times a second and a billion times and never and everywhere in between. So that when you're done doing whatever patching you're doing, oh, that was the other one, is you were busy patching it and the hardware spilled them to get them out and overwrote your patch. So you lost half of your GC moving pointer points and the other half you kept, but you lost half of them. And then the hardware, you know, reloaded the stale bits and the good bits, and you died that way. So you could have, you're patching the stack and the hardware overwrites you and you lose it. You have one where the hardware fetched before you got it done and halfway between everywhere. Fine, it's all fixable, but you have to be aware of it and you have to like dick around. Okay, if I force the hardware to dump, I know that it will not dump again. So I have to force the hardware to dump. Some of those machines we did like, not to mention Spark, we did call, which is push register. And there was a known hardware count of them you had to have varied by hardware cycle, a hardware version number. And that would force that register window to be dumped and the hardware would not be able to prefetch behind you. And then and the dumps were pretty quick and you just, 20 calls in a row, nested deep, all doing nothing except calling down the next one. Then you patched up here a little bit and then you unwound the 20 and you're good to go, whatever. But you had to have a magic trick every time. It differed by Azul hardware, from Titanium hardware, from Windows, Spark Windows, whatever. Everyone was different there. Okay, now I'm like the chat is like going crazy. Yeah, someone's finding what may be the JIT interface. Registration is N squared.
Yeah, if you look up anything about the GDB JIT stuff, you find the V8 folks and the GDB bug tracker. They're like, I noticed this thing causes up to second pause times. And the GDB people are like, stop registering so many functions. It's like, okay, well.
Matt, you've been discovered yet again. This is like the fourth time on this particular channel.
I think he's posted some of my blog stuff on Reddit, so
he neither confirms nor denies.
Yes. It's good to have some mysteries in life. Keeps the spice.
That's why you have an alt.
Okay, fair enough. I do funny things when no one's looking, like go to Burning Man. That's my spice in life.
Cameron does funny things like take your background.
Yes.
He is missing a cat though. The cat was behind.
Yeah. Well, varies. My cat comes across or doesn't.
I'm in a different time zone.
Cameron, you gotta let the cat out.
I like that. That's a good answer. All right, now that we've broken topic for a second, I'm going
3 hours ago, I had the cat behind me.
I'm going to throw out an unrelated thing.
Is it Schrodinger's cat?
Yeah, Schrodinger's cat. Yeah.
We can't answer that without killing him.
Yeah. It's a really old cat. And so at any moment, he's going to be dead in my bedroom or not. I won't know until I open the bedroom door and look.
I was going to say, if you haven't checked in a while.
Exactly. I'm grabbing it together a bunch of folks who are sort of senior theoretical people in Hindley Milner style typing systems, because I'm busy doing subtyping and lattice theory typing with Hindley Milner, and some folks have marched either ahead of me or very similar paths anyway. So I'm grabbing a bunch together Monday morning at 9 California time, UTC -7. If anyone's interested, let me know and I'll throw in on the Zoom chat. This first meeting's just going to be hi, hello, what's a better time? Do we know the right things? Are we talking the same language kind of stuff? But if you're interested,
happy to listen. Not sure I can add much.
Well,
that's
fine though.
Someone posted a link last week to bidirectional type inference.
Yeah, right. I've been.
So that's
doing my
turns
reading.
out to be almost, it's a subset of what we do, but that's basically the model that we, I had never heard of it before, but that's what we, that's
It's
what we
pretty
settled
well
on.
known technique. They don't claim they invented it. It's pretty well known technique.
Yeah, it's pretty
even
well
before
known by
they-
you guys who actually studied this stuff.
Right. It was new to me too. So I'm all happy to stare at it. And,
I didn't study it. But
so I'm going to talk to people who have been studying this, and they're going to tell me I'm stupid. I'm reinventing the wheel, and that's fine. And I'll happily
I just
take
I
my
just
lesson.
throw the link as an extra information because you can maybe post something on it.
I have to go find. I have a bajillion links open on my browser now. Let me grab.
For AA, are you considering a type that is basically A, make the type checker shut up so that I can do something temporary that doesn't make sense? So like Dart has type dynamic, which is a subclass of all types and a superclass of all types, and utter semantic nonsense, but also convenient.
Do the OCaml thing, obj.magic.
So I currently don't have unsafe planned out. Like I know I want to have an unsafe when I need to. I don't have an unsafe planned out. What I'm willing to do certainly is to say I'll take a thing whose type is abstractly sort of too broad and let you narrow it with a runtime cast. But I don't have that thrown in the language right now because I haven't run into it yet, but I haven't got my subtyping full on. And when I do, you'll obviously have to have a narrowing conversion.
Well, if all you're doing is narrowing, you can narrow with an if.
Yeah.
Are you this tight or something?
Yeah, right. Yes. This is not I'm not in theory planning to throw out I'll let you magically take a thing which I know to be a string and decide that it's a float. If it's a Persian, I'm going to convert it to a horse. I'm not going to do that. So when I say unsafe, that'll be your sandbox door opener. And if you have to, you can declare, I'm going to throw this widget into an unsafe memory, pull it out, but I'll demand you cast it. But that's a cast. It's a narrowing cast. I don't have currently a thing that's going to say,
So some languages have a sort of magic, I haven't done this yet, where you're just like, this integer equals question mark, question mark, question mark.
Oh, no,
I don't know, I'll put something here at some point.
Yeah, I'm going to use ... And that means if I execute this, stop and crash in the debugger with an unimplemented here, do something.
So that is a runtime assert, essentially.
That is a runtime, not an assert, which is turn on and offable. That is a runtime crash. That is a panic me now, I didn't write any code here.
Yeah, we call it to do.
To do, yeah, it's a to do.
Which goes back to the slick edit days where you would, if you used to do, it would automatically highlight.
Yeah, IntelliJ, if you write the word to do, IntelliJ highlights those.
IntelliJ copied all its editor features from Visual Slick Edit. So.
Excellent.
Beautiful.
Have you considered adding a bang, bang, bang that says this better be dead code at compile time or else there's a problem?
I have that, but I could add a specific syntax for it. The thing that you would say there is I put a type error in, and if it's not dead at compile time, the type error will throw a type error and you won't actually compile the program.
So everything's an expression in your work, right?
Yeah,
that helps because you want whatever the oh no, I haven't done this yet needs to be an expression.
Yeah, the GCC way of doing this is not the worst thing, where you put an annotation on the function that's like, this had better be dead, or this had better be unreachable, or this had better be inlined or not inlined, or blah, blah, blah.
Yeah. So a ... if you run it, you want it to die at compile time. No, you have to put a type error in. And the type error is to declare somebody an any type, not an all, which is the bottom of the lattice. Everyone's at least all or above. No one's an any unless they ain't executing. So you just, here is a type error. Declare 0 in any type. That :any is the type annotation, 0 is a 0, and that will fail. So it better be dead. So you might want a prettier syntax, I'll agree. But it's possible.
Yeah, if the semantics there, like syntax, you can figure out late in the game.
Yeah. I've long wanted to be able to have if def Windows, else if Darwin, else if Linux without having to do a macro assembler if def flavored things. So it'll be a runtime test. And if I can compile time prove if Windows, then you can have type errors in the not the Windows cases, and I'll be all happy because it's type errors. I mean, it's type errors, it's dead. So fine.
So what part of bidirectional type checking you overlap? A question to camera.
So I've only read the brief
right
in the brief start of the paper, and I am unclear where I sit in the land of things here. So I don't want to say this is where I do or I don't. I have a lattice, which is also a Boolean algebra, and has a couple other properties. Oh, bye-bye. And I do aggressive specialization, which covers a long ways, but doesn't count as parametric polymorphism. So then I go look at, and I've taken the Hindley-Milner algorithm and I have it turn into an incremental work list style so I can do partial evaluation while I'm doing my Hindley-Milner, which lets me have type errors. The Hindley-Milner will blow up on type errors and declare them dead at some point, and then I don't care. He blows up because it's in dead code, and he knows it too. He unifies with I'm dead now, and he didn't. And I don't care anymore. And I support.
Hindley-Milner uses unification, right?
I'm
uses unification, or
you talking about my Hindley-Milner or my?
Yeah, Hindley-Milner.
I am using unification. I support recursive types fully. So I'll handle the things that the occurs check blowout says recursive unification. I handle those and I produce a sensible type. You can't do sensible things with it, really. I've got a version that also now does records because I'm heading toward having a Hindley-Milner with memory state. And the record version does what my lattice side does, which will discover field names and field types, the correct way. Like I can recursively type both lattice and Hindley-Milner. I can recursively type a map call taking a linked list where you don't describe the linked list as a data type anywhere. I just discover it by the abstract way you're using the linked list, the structure, including all the recursive cycles and stuff. And I know I can do like tree-like things in lattice theory stuff. I assume my Hindley-Milner will do tree-like things, and that's probably a good test for today. But shortly, I'm going to move over to memory. And here I have a strong theory on the lattice side, and I don't know what to do with Hindley-Milner other than treat it as like a memory as a collection of records. Except the key difference is that I can't duplicate contents of memory ever. So I have to have some sort of linear logic. And here I don't know how to bring in linear logic in the Hindley-Milner yet, but that's sort of where I'm at. So I'll probably throw in a memory. I'll probably just make it a record of records. So it'll be a sort of straightforward addition.
You keep memory types separate from IO types?
Yes.
Because if I have a memory, I probably want to be able to serialize it across the network. And if I have an IO, that's not a thing.
Right. So I just keep IO as a separate thing because memory I can do all these optimizations on, and IO I do not. IO says I press the button, the missile launched. Right. World War III, we're all dead now, and I can't unwind. Right. Memory I can do all kinds of magic tricks with. IO I cannot. So IO is the infinitely threaded state. It only threads in and out, in and out, in and out, and goes through things and has to execute in order permanently. And memory I can of course shuffle loads and stores around and reorder and combine common loads and have a store of a value and a load get optimized and yada yada yada. Things happen there. So they're separate. Now, what can I do with memory in Hindley-Milner types? Well, okay, I want to do the declaration that it's a collection of objects. Okay. There's an approximation going on there where all objects of a particular alias class fold together. An alias class comes from a single allocation site. So I think that's entirely fair. And then I still have to have the property when I'm done that they're passed into every function call and brought out of every function call and otherwise serialized. You can't pass a memory around a function and have a different memory come out of the function, for instance.
So does a memory track some kind of a state?
Yeah.
Maybe.
Yeah,
Yeah.
it's tracking that. That's the point.
I remember that Cameron said Idris has a linear types, something like this at the type level. You can declare something that can be used only once or twice at the type level. And if you use it more than once and twice, it will give you a type error.
Right, that would be a linear logic style, which is what I want to be able to fold into Henley Milner and get the correctly typed answer out. I can go after the fact and say, and here I rely on a non-linear logic behavior, and so I have to throw a type error when I'm done, but that's not type discovery, really, right? So that's where I'm at. I'm getting close to memory, and on Monday I'm going to grab a bunch of folks and we're going to sort if there's a obvious path that I should have picked up long ago, or if we should meet again.
I would like to participate if I can.
Yeah, so send me a chat right now and I'll gather the chats, or send me an email or a Twitter or something. Write it somewhere and I'll find and scrape and.
Oh, okay. I will send you a mail. If yeah. Okay. Thank you.
Send me an email. I need the email, which I should be able to get from the
Okay,
Zoom.
email.
Yeah.
Okay.
And in fact, probably later today, I'll send out the invite. I sent one out to half people. I'll send it out again to whoever shows up here. Matt says, yeah, it's going to be 9 a.m. Monday morning, UTC -7, California, 9 a.m. California time. Okay.
You gonna throw it on YouTube after, like you do with these?
No, because I have a bunch of other people that I haven't interacted with before, and they're all over the world. So I will ask permission that the next meeting be videotaped. Okay, there you go. Yet another place I hadn't heard of. I'm like drowning them. UPenn. I grabbed somebody's programming language club from UPenn, and I'm throwing them in here. That's probably a better forum than the programming language club, because that's a meet and present thing, and we're all discombobulated time zones. I want a email-y thing to get started here. Fine.
So it's kind of late now, but I have a topic that I would propose for next week.
Yeah, we can go a little ways now, but fire away.
So I was listening to a talk from one of the guys who works on PyPy, and they do a tracing JIT. So they just have their interpreter, and then they have their JIT trying to JIT the interpreter interpreting whatever the code is.
We lost Max. He should hear this. It's fine.
So I was wondering what people thought of JITs that generate code specifically versus JITs that just JIT the interpreter. And the idea is you only write a new interpreter. So as Python changes, they only update the interpreter, and it saves you from, with HotSpot, you tended to have, here is my entire implementation as an interpreter, and then here's my entire implementation again as a JIT. And those were two separate things that may not agree on what a bytecode means.
Correct.
And keeping those consistent is non-trivial.
So the answer there is you look at the performance of C2 versus C1. And it's been about 30%.
Is C1 a tracing JIT?
It does that technology. It is not, but it's very similar in the code quality that comes out. And it's 30% faster for C2 versus C1 in terms of in runtime. Code generation, C1's 10x faster generating code. C2 is 30% faster executing code.
And there's a lot more that, because there was C1 and C2, there was also the JVM written in Java.
Yeah. And Graal.
And now there's Graal, exactly.
Right. Graal goes to C of nodes though, so they're not a tracing JIT either. So
yeah, Graal just generates code.
Yeah, it goes to C2. It does more inlining and more tracing smarts, but it's C2 style really. Tracing JITs, I will claim, lack key information you get from starting at better points and including a larger framework that lets you generate better code that turns into that 30% gain.
So you would say the trade-off there is probably, to some extent, the size of the language.
So Flavio's pointing
If you're
out,
doing an experiment where you're designing a new language, it might make sense to use a tracing JIT, so you don't have to write everything twice.
Yeah. What Max was doing, a template JIT first cut, you need an interpreter. Okay, they need a template JIT. That's a pretty good path for easy and quick upgrades. Tracing JIT's faster than a template JIT, and not terribly much more work. And then the next step up is you need to have like a heavyweight optimizer, which understands the boundaries of where things are, because he can make a lot more assumptions over a lot bigger area and get the next level of performance. So Flavio's pointing out that Graal's using tracing. I knew they were doing something with tracing for inline musicians. They have better inline musicians than C2. They have more information available to them. So I think that's a good plan, or some variation of that is a good plan to get better inline.
Graal doesn't just keep performance counters; it actually stores traces.
I don't know, but you can get, they're very similar. They're not the same, you're correct, but they're very similar, and they might drive to the same set of choices. Like the C2, C1 hierarchy thing keeps inline counters from whatever C1 did. So C1 did some level of inlining, those you can count as traced counters. C2 uses those traced counters, but they're not traces only. They took a C1 style thing, which did some level of inlining and has precision counters down these different paths. So different paths have precision counts, right? So one function got inlined 5 times in C1 and you get counts for them all. That's what C2 is using. So it's halfway. It's not really halfway. It's some distance towards what you would get out of an inline trace. Now, what performance gains do that better tracing knowledge feed into your inlining decision turn into in the end? I don't know, but I'm certain it's helpful. That seems a good thing to do. I don't know. Like tracing just for performance counters seems complicated, but if you already are putting in a tracing JIT as your first tier, then it totally makes sense, and you should absolutely run with that. So Max was doing a template JIT. If instead he did a tracing JIT, he would get better performance counters in general, which is fine, which was a good answer. And now if he goes to heavyweight JIT, he's got trace counters in hand. And maybe Graal did that. I don't know what Graal's low tier is. Yeah, and truffle is like a interpreter execution. That is a interpreter unroll thing.
Yeah, truffle is a language that you can write your interpreter in, so that Graal can then JIT your code.
Okay, so probably they're expecting truffle to do some amount of tracing of the interpreter-like state. That gives them tracing counters at least, which they throw into a sea of nodes plus better inline knowledge. It sounds like a good plan to me.
Yeah, it's probably not a crazy start if you want to experiment with a language to try and write it in truffle so that you get the benefits of Graal and reasonable speed for.
Yeah. Graal's still, it's getting close. It's playing catch up to C2 and it's getting close. But it's been getting close for like 20 years. Those guys had a long uphill fight, and I think they're actually sort of seriously competitive now. They're not like they win here and they lose here, and they only show the benchmarks where they win, and they have potholes they fall into they don't want to talk about, and then you fall into the pothole and things get 10x slower because you failed a JIT and and C2 got those beaten out a long time ago, but at this point, 6 one half dozen other.
I mean, C2 is not a low bar.
Apparently not.
It's a different org as well, so it's a completely different mindset. Graal comes from the Sun Labs group, which is it's like a completely different world.
Those guys for many years.
Yeah, but the development methodology is dramatically. Yeah, I'm not going to say incompatible, but different.
Can you express that difference in some way?
Not without getting sued, no.
I probably can, but I'd be curious to hear Cameron's.
So the Sun Labs group is academic. They're all PhDs times 10. When Cliff was going to work, they were going back for their third PhD. So a lot of interns from doctoral programs as well. And they roll up into part of the organization that is not profit driven.
Yeah.
So, which is unusual in Oracle. And And 99% working is good enough to ship.
Yeah.
Which, as you know, when you're compiling a couple trillion lines of code per second forever, because you're being used by 10 million developers and pretty much everything out there, 99% is a lot of bugs.
Yeah, exactly.
So there's some teething issues, but
20 years ago, I debugged a bug that happened on Deutsche Bank's main trading floor. When I first found it, out of, once per year, but one of those times was on Deutsche Bank's main trading floor, where they went to Sun and said, we will not pay you another penny until you root cause this bug. And I had debugged that bug once on my desktop, too late for the patch to ship that version. Once in their last minute, they're testing, and they found it again. But this was like 6 months later, and I debugged it. It took me 2 weeks because you only had a core dump. Debug it, discover it, and say, I have the root fix. They said, too late, we're going to ship. Hit Deutsche Bank. A year later, they fell over, and they went back, and I spent another 2 weeks debugging it and saying it's the same bug. It just sucked. But you had to do them. You tracked down those bugs that you did not want to deal with. Here's a core dump of HotSpot from last year. Why did it crash? Oh, geez.
Yeah, the guy who does SQLite talks about that he's like, we thought we were taking this seriously and had gotten all the bugs out. And then they decided to include it as a key part of airplanes. And we had to meet all of the aviation safety standards and found a bunch more bugs and fixed them. And then we thought we had all the bugs out.
Yeah.
And then they included it as a core part of Android and ran it on 4 billion devices. And they got a whole bunch more bugs.
Yeah, yeah.
Like, fun story, run your software on 4 billion devices with inconsistent hardware. You'll learn something.
Well, that's where I've been with. By the time I left Sun, it was already on millions and millions of machines. And now it's on billions and billions of machines. There's some hardcore, things are beaten out now, but holy moly, it took a while. And there were some long tail, low frequency bugs that.
Yeah, if you want to find the 6 sigma problems, you need to run it 1,000,000 times. If you want to find 9 sigma problems, you need to run it 1,000,000,000 times.
Yeah, it was tough. All right, now I think we have a good wrap-up point. So if you're excited to talk with more theoretical guys on type systems, send me a mail. And otherwise, I'll see people in a week.
Thanks.
Okay. It was good fun. Bye-bye.
Bye.